The next two lectures will be by Professor Jack Sweat. He is professor in the Department of Chemistry, Biochemistry and Physics at the University of Quebec, Trois-Rivières. This is in Quebec, Canada. Professor Jacks, he is well known for his work. He is a renowned scientist working in the field of metal hydrides.
Hello everybody. My name is Jacques Huot. I'm a professor at the University of Quebec at Trois-Rivières and also member of the Hydrogen Research Institute. Today we will talk about tailoring metal hydride for practical application. This is in two parts. The first part will be nanostructure in general, and the second part will be on the effect of nanocrystalline structure on the capacity of metal hydride, and also some other method to get nanostructure materials. So just a quick recap on what our metal hydride. You could consider metal hydride to be like a kind of hydrogen sponge. So in a metal hydride, you have a chemical bond with the metal atom, and the absorption is an exothermic reaction, and the desorption is an endothermic reaction. So to give you some idea of the difference, but with metal hydride with respect to the other ways to store hydrogen. So if you store hydrogen as a gaseous form at 1 bar at room temperature, you see that the volumetric capacity is quite low. In order to increase that, you have to increase the pressure. So if you go to 150 bar, you have a much better volumetric capacity. And if you are using liquid hydrogen, so usually if you want to transport a huge quantity of hydrogen, liquid hydrogen, in my opinion, liquid hydrogen is the best way. Of course, it's at low temperature at 20 K, but you see that the volumetric capacity is quite good. But you see for metal hydride here, you have a high temperature metal hydride and you have a low temperature metal hydride. So this metal hydride is working at room temperature. This one is working at least 300 degree, 350 degrees C. And you see that actually it's a little bit counterintuitive, but you see that the volumetric capacity of hydrogen is higher in a metal hydride than in a liquid. So the hydrogen atoms are more compact in a metal hydride than in a liquid. It's counterintuitive, but this makes this is one of the best advantage of metal hydride, is that hydrogen is compact, so your tank will be very small. But the disadvantage, as you see here, is that the gravimetric density is quite low. So here, this means that you only have 7.7 weight% of hydrogen in a metal hydride tank made of magnesium hydride. Okay. And the rest is just the weight of magnesium. And for lanthanum nickel 5, it's even worse. It's only 1.4 weight%. So that's one of the big disadvantage of metal hydride. So the advantage and the disadvantage, well, you see that for metal hydride, the advantage, as we said, it's high volumetric density. It could work at low pressure, but the reaction of desorption is endothermic. So why I list it as an advantage is because if you have a hydrogen metal hydride tank, in your car and you have an accident and the tank is ruptured and you have hydrogen getting out and hydrogen is taking fire. So then it will heat up the tank, but as the tank is heating up, it will desorb hydrogen, but as it desorb hydrogen, because the reaction is endothermic, it will have a tendency to cool itself. So it will kill the reaction by itself. So this is inherently safe. The disadvantage is usually you have a high temperature of operation. If you want to have a good capacity, for example, with magnesium hydride, you have to work at high temperature, more than 300 degrees C. Usually the hydrogen sorption kinetic, dehydrogenation is relatively slow. The cost, depending on the material, it could be expensive, and again, you have to consider not only the cost of the raw material, the cost of the alloy, but also you have to consider the cost of, loading the alloy with hydrogen and putting that in the tank and so on. So the process cost could be quite expensive. So you have to take that into account. And pyrophoricity, because metal hydride, after many cycles of hydrogenation, dehydrogenation, they will turn into very, very small powder, and any powder that is very, very small could be pyrophoric. And also for metal hydride, because they react with hydrogen, so it means that they could react with oxygen also. So you could have problem of pyrophoricity. So very quickly, just the step for forming hydrogen metal hydride. So first you have hydrogen in gas phase, and this hydrogen has to be split into two hydrogen before entering, because on a metal hydride, what is stored is not a molecule H2, but it's a proton. It's the hydrogen atom. Okay, so first you have to break this molecule. After that, the hydrogen has to break. Usually you have a small oxide layer on the surface of your alloy, so it has to break this oxide layer. And for hydrogen, first you have to be in adsorption, so you adsorb on the surface, and then it split in two, and and then the proton will enter the hydrogen, the metal, and first it will form in solid solution, so it will just go into the metal structure. But as the pressure of the gas is increasing, then the concentration of hydrogen in your metal will increase up until you nucleate the metal hydride phase. And in that phase, then the hydrogen will go on specific site depending on the crystal structure. It could be on an octahedral or a tetrahedral site. And you have a lattice expansion. It could be up to 30% of expansion of your lattice, of your metal. So that's the thermodynamics. So you have your metal, and this is the pressure of hydrogen. This is the capacity of hydrogen. So it's the number of hydrogen atom over the number of metallic atom. And as you start, you increase the pressure, hydrogen will enter in solid solution in your metal up until you reach that point. At that point, you start to nucleate the metal hydride phase. Okay, so usually it has a different crystal structure. And now that you have a new phase in your system, by the law of Gibbs, so if you have a new phase, it means that you are losing a degree of liberty. So if you are losing a degree of liberty, it means that the capacity could increase even if the pressure doesn't increase, because as the pressure tries to go up, you have more hydrogen that will go into the metal hydride, okay, that will form the metal hydride. So on this plateau, you go from 100% metal and 0% hydride up to here, where you have 100% metal hydride and 0% metal. And here it's 50-50, okay? So you have the transformation along that plateau. You have the transformation from the metallic state to the metal hydride state. And once all your material, all your alloy is on a metal hydride state, then you are losing one phase. You are losing the metal phase. So you are gaining 1 degree of liberty, and then to increase the capacity, the pressure has to increase. And here, hydrogen will enter in solid solution in the metal hydride. So, and of course, this is a standard phase transition. So depending on the temperature, the plateau pressure will change. Okay, so you could plot the logarithm of the plateau pressure as a function of 1 over T, and the slope will give you the enthalpy of the reaction, and the ordinate at the origin will give you the entropy of your reaction. So one advantage of the metal hydride is that it could span a large range of application, from portable and mobile up to something as big as the fuel cell submarine. So I don't think if you have like a micro fuel cell with a smartphone, you could not store hydrogen in a liquid phase. It doesn't make sense. You could not have a reservoir at 20K in your pocket. And the same thing with pressure. You could not have a small tank at high pressure, because the amount of hydrogen that you need for this is very, very small. So the tank will be almost as big and as heavy as the device itself. So it doesn't make sense. So and the same thing up to the submarine. For the submarine, well, what is important for them is space. They don't have a lot of space, so they need something that will store hydrogen that will not take space. And for them, weight is not a problem. Okay, it could be heavy. It doesn't matter for a submarine. So this is why the choice of storing hydrogen for a fuel cell submarine is metal hydride. So metal hydride for practical application. So presently, all known metal hydride suffer some limitation for practical application. Either they are too expensive, or the capacity is too low, or they lose capacity during cycling, or the temperature and the pressure of operation is not right for your application. So most of the time, the metal hydride are not ideally suited for practical application right now. So the goal is to modify this and to try to find metal hydride that will really meet the specification for practical application. So how to solve this limitation? Well, we are trying to find new alloy, or we could modify existing alloy. And nano sizing is a way to obtain new alloy and also to modify the existing alloy. So you could the existing alloy, as we will see, if you have a conventional alloy, but you make it in the nanocrystalline dimension, then the characteristic will change a little bit. So it could make your alloy attractive for practical application. So how to do nanostructure in metal hydride? Well, there is two ways as for any metal. So it's either bottom up or top down. So bottom up is that you construct the nanocrystalline alloy directly. So you could do that by cold vapor deposition, thin film, and so on. So you start and you more or less you assemble atom per atom until you get your nanocrystal. But in my opinion, this is not so suitable for scaling up. You could not produce ton of material with this, but these are techniques that are very interesting from a fundamental point of view, because you could really control the size of your material, and also the chemistry and so on. So you have more control on your sample, and it makes the understanding, and it makes the study much easier. Okay, so these are interesting technique, but we will not discuss them in this course. So what we will discuss is the top down. So you start from a polycrystalline material and you reduce its chrysalid size. So this is what we will study in this course. So there are many ways to do that. You could do that by ball milling, cold rolling, equal channel, angular pressing, high pressure torsion, and so on. So we will discuss some of them in this course. So nanostructure metal hydride. So getting a nanostructure metal hydride could solve some of the practical problem. For example, the kinetics or the first hydrogenation. So we could make the first hydrogenation much faster, and you could make the alloy much easier to cycle. So after many cycles of hydrogenation, you will not lose so much capacity. So what is the definition of a nanocrystalline material? Well, the classical definition is that your chrysalid size should be less than 100 nanometer. So the chrysalid size is the coherent domain of your crystal, okay? And in a nanocrystalline material, you have a lot of defect. So these defects could act as activation, nucleation site. So they will lower the activation barrier. So if you have more nucleation site, your kinetic will be faster. And also, depending on the size of your grain boundary and the size of your nanocrystallite, you could have a grain boundaries could make up to 30% of your material. And these grain boundary could serve as a hydrogen pathway. So hydrogen could go through these grain boundary to reach your nanocrystalline material. And all of this will make that the kinetic will be much faster in a nanocrystalline material compared to a polycrystalline material. So today we will look mainly at ball milling to prepare metal hydride. This is the technique that is used by most of the researcher in the field of metal hydride. So almost all of them are using ball milling to get a nanocrystalline structure. And as we saw, by ball milling, you could have defect. So that will increase the nucleation site. You could have formation of the metastable phase. This is a common feature of ball milling. So not only in metal hydride, but also in other type of material. Usually you could get a metastable phase, a high pressure, high temperature phase, just by ball milling at room temperature. Of course, you could synthesize nanocomposite, so you could mix two alloy, and you could get a nanocomposite. Usually when you do ball milling, the particle are of the order of the micron, but the crystallite are order of nanometer. So you have to be careful when we talk about nanocrystalline material. It doesn't necessarily mean that the particle are nanocrystalline size. It's the crystallite that are nano size, okay? And sometime in the literature, you see people are talking about grain size, but I don't like to use this word because for some people, grain may mean particle, and for some other people, grain may mean crystallite. So I prefer to talk about particle and crystallite. And then it's clear for everybody. So if you talk about particle, that's a particle, okay? So that particle could be of the order of micron, but it's made of many small crystallite of the order of nanometer. And of course, by ball milling, you could increase the specific surface area. So ball milling, very schematically, so in ball milling, you have a crucible and you put your raw material in form of powder, and you have balls that are made of stainless steel, hardened stainless steel, or tungsten carbide, or some other material. You select the material depending on what you want to ball mill, and you shake this crucible, and then you will have a collision between two particles, or between a particle and the wall of your crucible. And of course, if you have powder in your crucible, then you will have powder that is trapped between two balls, or between a ball and a wall. So when the two balls collide, you have your powder that is here will be broken. Okay, so you will have, or they could be cold work, a cold weld. Okay, together the two particles could be cold weld with the force of the impact of the two balls. So it's a repetition of fracture, cold welding, fracture, cold welding, and so on. And after you repeat that many times, you will have a nanostructure material. So today I will show you milling of magnesium hydride. Magnesium hydride, well, it's a well-known hydride. It has a high capacity, 7.68%, and it's relatively low cost because it's abundant in the earth crust. The disadvantage is that it has a high temperature of operation, more than 300 degrees C. Usually the first hydrogenation is very difficult, and also the kinetic is relatively slow. Okay, so what I will show you today is that the ball milling of commercial magnesium hydride that we ball mill in a high energy milling machine. So this is the powder before milling and after milling 20 hours. So you see, and the scale is not the same. Here this is 30 micron, here it's 7.5 micron. So you see that before milling, the particle are like smooth, okay, the surface is smooth, but you see here after milling, the particle are smaller because this is only 7.5, but these are the big one. I have smaller one here. So you have a strong reduction of particle size. And also you see that, for example, this particle is an agglomeration of smaller particle. So sometimes by ball milling, you will break particle, but also you will tend to fuse particle together. Okay, and you see that the specific surface area here was only 1.2 square meter per gram, and by ball milling we increase it almost by a factor of 10, but it's still not a very high specific surface area. So you increase the specific surface area by an order of magnitude, but it's still not very high like you see in carbon nanotube or graphite or so on, where you have 100 and 1,000 square meter per gram. So this is the powder diffraction. The on mill is here, and after 2 hours you see that the break peak are getting broad, so that means that it's a nanocrystalline structure, and you see that these peaks are appearing. Okay, that we did not have these peaks in the on mill, and the mill one you have these peaks. Well, these peaks actually are this phase, so this is a metastable phase of magnesium hydride. So the normal phase is the beta phase, that's the room temperature phase, but the gamma phase is the high temperature, high pressure phase. And you see that you could synthesize it just by ball milling at room temperature. So if you look at, if you do a Rietveld refinement, if you analyze these patterns, then you see that after milling, you have 74% of magnesium hydride and 18% of the metastable phase of magnesium hydride. And you see a reduction of the chrysalid size. So now it's only of the order of 10 nanometer. So while before it was polycrystalline, so it was more than 100 nanometer. So if we look at the hydrogenation characteristic, so you see, so this is on mill is the fill mark and mill is the hollow mark. So this is the on mill, this one, and this one. And so you see, for example, at 573 degree K, the on-mill one is really not desorbing. It doesn't want to desorb, but at the same temperature for the mill one, you see it started to desorb. And if we look at 623 K, so 350 degrees C, so this is the desorption of the on-mill one, and you see the mill one is here. It's much faster. It's totally desorbed in 800 seconds, so about 12 minutes. While here, after half an hour, it's still not fully desorbed. And you see even the on-mill one at 648, it's still slower than the mill one at 623. So you see that ball milling, just getting a nanocrystalline structure, drastically improve the kinetic of the desorption kinetic and also the hydrogenation kinetic. So you have the same thing here. So for example, at 573, so this is the absorption, and after half an hour, it's not fully absorbed, and you see that this one is fully absorbed about in maybe 12 minutes, 800 seconds. Okay, it fully filled. So you see again that nanocrystalline makes the hydrogenation and dehydrogenation much faster. But this is the thermodynamics. So this is the pressure composition isotherm, as we saw in one of the first slide. So this is the on-mill one. So the on-mill one, you have your plateau, as we saw in the first slide. And then you have, so this is the absorption. And after that, you have the desorption and you have a plateau again. So the plateau on absorption and desorption are usually not at the same position. This is what we call hysteresis. But this hysteresis depends on many factors, but also on the kinetic. So you see that this is not a flat plateau, because here, in principle, at this point should be a stable point. Okay, so you should have equilibrium at this point. But how do you define equilibrium? You define equilibrium when the pressure doesn't change. Okay, so you expose your material to that pressure, and then you see that the material doesn't absorb hydrogen anymore. So you say, well, this is on equilibrium. But if the kinetic is very slow, then the kinetic is so slow that your apparatus think that you reach equilibrium when actually it's not at equilibrium. So this is due to the very slow kinetic. But as we saw, when you do ball milling and you get a nanocrystalline structure, the kinetic is much faster, and you see that your plateau now is flat, okay? Because the kinetic is faster, and also this plateau move up to here, so the hysteresis is much less. Because you could see here for the on-mill one, you see that it start to bend here, but the kinetic is so slow that it doesn't reach the equilibrium point. Okay, so and so this is why this plateau is lower. So this is not due to thermodynamics. This is due only to kinetic. Okay, so but you see that you basically do not change the thermodynamics, and you just change the kinetic, and you see a small reduction of capacity here after ball milling. So this is confirmed by calorimetry. So this is under hydrogen pressure. So that was under 2 bar of hydrogen. So if you put your magnesium hydride and you start to increase the temperature, at one point it will desorb, and that gives you that peak. And that's the temperature of the peak. Okay, and if you ball mill, then you reduce that temperature because the kinetic is faster. Okay, and you notice that here I have only one peak, and here I have 2 peaks. But you remember that in the ball mill material, we had 2 phase. We had the gamma phase and the beta phase. So that's why I have 2 peaks here now. One of them is the desorption of the gamma phase, and the other one is the desorption of the beta phase. Here I just have the beta phase, but you see a reduction of that temperature peak. So so it means that I have a reduction of the activation energy. So we could measure that, and what we measured that for the on-mill, for this one, the activation energy was 156 kilojoule per mole, while for the mill one, it was 120. So that's one of the reasons why the kinetic is faster, because the activation energy is lower. So the conclusion for the magnesium hydride, so by ball milling, we found that you could have nanocrystalline material with a metastable phase. And after ball milling, the particles were still of the order of micron, but much smaller than before milling. And you have a tenfold increase in the specific surface area. You have a faster hydrogenation and dehydrogenation, and a reduction of the activation energy. So this improved the kinetics, and also because we have defect and the small particle size and the increase of specific surface area. So these are all features that will make your kinetic faster. Okay. So reduction of activation energy, smaller size, defect, and so on. So, but we also saw that intensive milling does not alter the thermodynamic properties of magnesium hydride. And this is a common feature in nanocrystalline material. Usually you do not change the thermodynamic unless you're going to very, very low, very, very small crystallite size. So for example, for magnesium hydride, you have to go to the thermodynamic starts to change at about 7 nanometer, and just a little bit. In order to have a good change of thermodynamics, you have to reach like 2 or 3 nanometer, and this is not the type of size that we get by ball milling usually. So it's much too small. So in principle, by ball milling, usually you do not change the thermodynamics. So with this will conclude this part 1, and in part 2 we will see. So here we mainly see the effect on kinetics, but in part 2 we will see the effect on capacity, and also we'll see some other ways to make nanocrystalline metal hydride. So thank you very much for your attention.